Hello everyone, I'm Shrishti. I have reviewed and analyzed the paper on BlinkDB. This paper is written by Samir, Aurojit, Henry, students at University California, Berkeley, Bazan, student at MIT, Ian, researcher at Conviva Incorporation. Increasingly, new applications demand near real-time response rates. Modern data analytics applications involve computing aggregates over a large number of records to roll up web clicks, online transactions, content downloads, and other features along with a variety of dimensions, including demographics, content type, region, and so on. Traditionally, such queries have been executed using sequential scans over a large fraction of a database. Many of these applications can afford to trade result accuracy for response time and space. The examples of such problems are update ads on a website based on trends in social networks like Facebook and Twitter, determine the subsets of users experiencing poor performance based on their service provider or geographic region. BlinkDB is a distributed sampling-based approximate query processing system that strives to achieve a better balance between efficiency and generality for analytics workload. BlinkDB allows users to pose SQL-based aggregation queries over stored data, along with response time or error-bound constraints. As a result, queries over multiple terabytes of data can be answered in seconds, accompanied by meaningful error bounds relative to the answer that would be obtained if the query ran on the full data. BlinkDB integrates these two ideas to Apache framework of Hive Query Engine and Shark. The two ideas are first, to build and maintain a set of multi-dimensional stratified samples from original data over time. Second is the dynamic sample selection strategy to trade off accuracy with higher response time. Dynamic selection of subsamples from stratified samples are constrained by the user query. Example of the user query. Here, the user query is constrained by error and the confidence rate. Here, the user query is constrained by the response time. BlinkDB is built on top of Hive Query Engine, which supports both Hadoop MapReduce and Spark via Shark at the execution layer and uses the Hadoop distributed file system, which is HDFS, at the storage layer. The image here shows the overall architecture of BlinkDB. BlinkDB extends the Apache Hive framework by adding two major components to it. First, an online sampling modules that creates and maintains samples over time. Secondly, a runtime sample selection module that creates an error latency profile for queries. Here we will talk about those two steps. BlinkDB extends the Apache Hive framework by adding two major components to it. An online sampling module that creates and maintains samples over time. To decide on the samples to create, we use the QCS, which is query column sets that appear in the queries. Once this choice is made, we rely on distributed reservoir sampling or binomial sampling techniques to create a range of uniform and stratified samples across a number of dimensions. At the runtime, we employ ELP, which is error latency profile, to decide the sample to run the query. The ELP characterizes the rate at which the error decreases as the size of samples on which the query operates increases. It is used to select a sample that best satisfies the user constraints. BlinkDB also augments the query parser, optimizer, and a number of aggregation operators to allow queries to specify bounds on error or execution time. Sample creation techniques involve two steps. First is creation of stratified sample for a single query, then optimizing this created sample for all the future queries. So our selected sample work with all the future query without making changes to the existing samples. Second step is to optimize the sample on the basis of three parameters: sparsity of data, workload of data, and storage. A problem is formulated and solved to optimize these parameters. We will go in detail with each of these steps in the upcoming slides. Queries that do not filter or group data often produce accurate answers when run on uniform samples. However, uniform sampling often does not work well for queries on a filtered or group subsets of the table. When members of a particular subset are rare, a large sample will be required to produce high confidence estimates on that subset. A uniform sample may not contain any member of that subset at all, leading to a missing row in the output of the query. The standard approach to solving this problem is stratified sampling, which ensures that the rare subgroups are sufficiently represented. The standard approach is uniform sampling, takes the sample with equal probability. It is important to understand why this is an imperfect solution for queries that compute aggregates on groups. A uniform random sample allocates a random number of groups to each group. The size of one group present in the uniform sampling is proportional to the size of that group in the original dataset. But if we care about the error of each aggregate equally, it is not clear why we should assign more samples to few groups just because they are largely present in the original dataset. Choosing sample sizes at random introduces the possibility of missing or severely underrepresenting groups. The probability of missing a large group is vanishingly small, but the probability of missing a small group is substantial. This problem has been studied before. Briefly, since error decreases at a decreasing rate as sample size increases, the best choice simply assign equal sample size to each groups. In addition, the assignment of sample size is deterministic. Count of each group in the dataset is computed and the rows are equally and uniformly selected from each group without replacements to form a stratified sample. The chart here shows stratified sample associated with a set of columns. Prior work which focuses on single column stratified samples or on a single multi-dimensional stratified sample. BlinkDB creates several multi-dimensional stratified samples. Each stratified sample can potentially be used at runtime to improve the accuracy and latency, especially when the original table contains small group of particular column set. However, each stored sample has a storage cost equal to its size, and the number of potential samples is exponential in the form of columns. As a result, we need to be careful in choosing the set of column sets on which to build stratified samples. We formulate the trade-off between storage cost and the query accuracy as an optimization problem. Finally, we return two important constants to the query engine. We set their values to 1 lakh as the experimental result shows the system works best on these values. The picture alongside shows the dynamic subsample selection from the whole stratified samples selected after executing the optimization steps. BlinkDB runtime steps includes selecting the sample. This step involves choosing an appropriate sample for a query primarily depends on the set of columns that occur in its where or group by clauses and the physical distribution of data in the cluster. If BlinkDB finds one or more stratified samples on a set of columns, BlinkDB simply picks the sample with the smallest number of columns and runs the query. Selecting the right sample size. Once a set of samples is decided, BlinkDB needs to select a particular sample and pick an appropriately sized subsample in that sample based on the query's response time or error constraints. This is accomplished by constructing an error latency profile for the query. The ELP characterizes the rate at which error decreases with increasing sample sizes and is built simply by running the query on smaller samples to estimate the selectivity and a project latency and error for larger samples. Bias correction. Running a query on a non-uniform sample introduces a certain amount of statistical bias in the final result, since different groups are picked at different frequencies. In particular, while all the tuples matches a real subgroup would be included in the sample, more popular subgroups will only have a small fraction of values represented. To correct for this bias, BlinkDB keeps track of the effective sampling rate for each group associated with each sample in hidden column as a part of sample table schema and uses this to weight different subgroups to produce an unbiased result. BlinkDB is built on the top of Hive Query Engine, both supports Hadoop and MapReduce and Spark via Shark at the execution layer and uses the Hadoop distributed file system at the storage layer. This implementation stack is shown alongside. The implementation required changes in the few key components. We add a shim layer to the Hive QL parser to handle the BlinkDB query interface, which enables query with response time and error bounds. Furthermore, the query interface can detect data input, triggering the sample creation and maintenance module, which creates or updates the set of random and multidimensional samples. We further extend the Hive query parser to implement a sample selection module that rewrites the query and iteratively assigns it an approximately sized uniform or stratified samples. We also add an uncertainty propagation module to modify all pre-existing aggregation functions with the statistical closed forms to return error bars and confidence levels in addition to the result. Concerns with BlinkDB. One concern with BlinkDB is that multiple queries might use the same sample, inducing correlation among the answer to those queries. For example, if by chance a sample has a higher than expected average value of an aggregation column, then two queries that use the sample and aggregate on that column will both return high answers. By contrast, in a system that creates a new sample for each query, a higher answer for the first query is not predictive of a higher answer for the second. However, as we have already discussed, pre-computing samples is essential for the performance in a distributed setting. We address correlation among query results by periodically replacing the set of samples used. BlinkDB runs a low priority background task which periodically samples from the original data, creating new samples which are then used by the system. An additional concern is that the workload might change over time and the sample types we compute are no longer optimal. To alleviate this concern, BlinkDB keeps a track of statistical properties of underlying data, which are variance, percentiles, etc., and periodically run the sample creation module to recompute these properties and decide whether the set of samples needs to be changed. To reduce the churn caused due to this process, an operator can set a parameter to control the percentage of sample that can be changed at any single time. To evaluate the performance of BlinkDB on real time, we are setting up two experiments. The Conviva and the TPCH datasets were 17 TB and 1 TB in size respectively, and were both stored across 100 Amazon EC2 nodes, extra large instances. The cluster was configured to utilize 75 TB of distributed storage, disk storage, and 6 TB of distributed RAM cache. Conviva workload. The Conviva data represents information about video streams viewed by internet users. We use query traces from their SQL-based ad hoc query system, which is used for problem diagnosis and data analytics on a log of media accessed by Conviva users. These access logs are 1.7 TB in size and constitute a small fraction of data collected across 30 days. Based on their underlying data distribution, we generated a 17 TB dataset for our experiment and partitioned it across 100 nodes. The data consists of a single large fact table with 104 columns such as customer ID, city, media, URL, genre, date, time, users, OS, browser type, request response time, etc. The 17 TB dataset has about 5.5 billion rows and shares all key characteristics of real-world production workloads observed at Facebook or Microsoft. TPCH workload. We also ran a smaller number of experiments using TPCH workload to demonstrate the generality of the results with respect to a standard benchmark. All the TPCH experiments ran on the same 100-node cluster on 1 TB of data. The 22 benchmark queries in TPCH were mapped in a unique query column. The solutions. First, we compare BlinkDB to query execution on full-size dataset to demonstrate how even small trade-off in accuracy of final answers can result in order of magnitude improvements in the query response time. BlinkDB significantly outperforms its counterparts by a factor of 10 to 200 times because it is able to read far less data to compute a fairly accurate answer. For both data sizes, BlinkDB returned the answers in few seconds as compared to thousands of seconds for others. So the other counterparts are Hive, Shark, or MapReduce. Here is the chart which shows the response time for all four of these. Second, we evaluate the accuracy and convergence properties of our optimal multi-dimensional stratified sampling approach against both random sampling and single column stratified sampling. Here is the chart for both the datas which are taken from Conviva and TPCH. Third, we evaluate the effectiveness of our cost models and error projections at meeting users' accuracy response time requirements. This is our convergence model, how user has requested, the error boundations and time boundations, and how we have performed on it. Finally, we demonstrate BlinkDB's ability to scale gracefully with increasing cluster size. Here is the chart. Prior work on interactive parallel query processing framework has broadly relied on two different sets of ideas. One set of related work has focused on using additional resources like memory or CPU to decrease query processing time. Examples include Spark, Dremel, Shark. While these systems deliver low latency response time when each node has to process a relatively small amount of data, they become slower as the data grows unless new resources are constantly being added in proportional. Additionally, a significant portion of query execution time in these systems involve shuffling or repartitioning massive amount of data over the network, which is often a bottleneck for queries. Another line of work has focused on providing approximate answers with low latency, particularly in database systems. Approximate query processing for decision support in relational database has been the subject of intensive research and can either use samples or other non-sampling based approaches. Sampling techniques here uses either single stratified sampling technique, which we have already compared to BlinkDB's multiple stratified sampling technique. Sampling techniques used in the examples also do not guarantee error margin or are just much suitable for ad hoc workload. Online aggregation, OLA, and its successors propose the idea of providing approximate answers which are constantly refined during query execution. It provides user with an interface to stop executions once they are satisfied with the current accuracy. As commonly implemented, the main disadvantage of OLA system is that they stream data in a random order, which imposes a significant overhead in terms of input and output resources. Naturally, these approaches cannot exploit the workload characteristics in optimizing the query execution. Pros and cons. Pros: BlinkDB is faster than existing distributed systems for same amount of resources. It provides bounded error rates and response time. For little trade-off in the accuracy, it multiplies the response time, close to near real response time. Simple subsets of SQL queries are easy to understand. Doesn't need to learn a new technology. It scales better than other related work in existing technologies. Cons: BlinkDB is prone to the problem of correlation, and to address which it requires storage overheads. To address the problem of change of workload, BlinkDB would need overhead to compute variances, percentiles, etc. in the background to keep the data optimal. Techniques like online aggregation could be added to BlinkDB to make it continuously refine the values of aggregates. Such techniques are largely orthogonal to the idea of optimally selecting pre-computed stratified samples. The below 6 listed techniques: materialized views, data cubes, wavelets, synopsis, sketches, histograms. These techniques are mostly applicable when the future queries are known in advance. Nonetheless, these techniques are orthogonal to BlinkDB, as one could use different wavelets and synopsis for common queries and resort to stratified sampling when faced with an ad hoc query that cannot be supported by the current set of synopsis. For instance, the join synopsis can be incorporated in BlinkDB, where any join query involving multiple tables would be conceptually rewritten as a query on a single join synopsis relation. Thus, implementing such synopsis alongside the current set of stratified samples in BlinkDB may improve the performance of certain cases. Incorporating the storage requirement of such synopsis in our optimization formulation makes an interesting line of future work. That's all. Thank you.